Okay, in the preceding, I had my subscripts backwards from here on. And we fixed that, and that might have been a little confusing, but you can see the right triangle that we get when we do the scalar projection. And that for the F12 vector, this vector, the projection onto the velocity is going to be this. It is going to have this magnitude. The scalar projection will be square root of 3 over 2 times F12, where F12 is the magnitude of the F12 vector. And the parallel component, or the perpendicular component, the component perpendicular to V1 is going to be 1/2 F12. And over here, you get this picture. The scalar projections will be negative square root of 3/2 times F21 and negative 1/2 times F21 because of the orientation of this vector being at 210 degrees with the velocity vector. Okay, so if we put the vector components into a picture, we have our two projections, our two now vector projections, here and here. And we have our two parallel or perpendicular components here and here. And they're labeled correctly, F12 perpendicular, F21 perpendicular. They're equal and opposite, as is obvious from a picture, but we also get it if we do the trigonometry with our 210 degree angle. Then we have F12 parallel and F21 parallel, equal and opposite in the direction of our velocity. Okay, since the magnitudes of F12 and F21 are equal, because they're equal and opposite forces, all the components are equal and opposite. Because why? Because we got a square root of 3 over 2 here, a negative square root of 3 over 2 here. Those two scalar projections are equal and opposite, so the vector projections will be equal and opposite. And the parallel, or the perpendicular components, are also equal and opposite. And from that, we get that the net force on the two-mass system, the system consisting of the two balls, is 0. Okay? Now that has profound implications that we ended up not actually talking about today. I'll just kind of foreshadow a little bit and say, well, the implication there, if the net force in the system is 0, by the impulse momentum theorem, which we talk about in a few minutes, the momentum of the system isn't going to change. Now, we kind of show the same thing in a little different way, and it's going to be very consistent with the statement I just made. Okay, so we kind of work toward that statement by asking, okay, what's the acceleration of the first ball? That's what's the acceleration of mass 1. And we say, well, in the ideal situation, which I stated as being the table has no friction, so the normal force and the gravitational forces are going to all be equal and opposite, and there's not going to be any friction due to the normal force between the ball and the table. Now, there's going to be plenty of stuff that happens due to the normal force between the two balls while they're in contact, but we already talked about that. That means that F21 would be the net force on M1. That would be the only force acting on this mass. The F21 force is the only force acting on the mass. There's no friction. Gravity is balanced by the normal force of the table on the ball. So if that's true, then Newton's second law tells us that the acceleration is going to be, well, Newton's second law says that F21, the net force on this ball, is equal to the mass of the ball times its acceleration. So its acceleration is equal to the net force divided by the mass, F21 being the net force. So if F21 is a net force, there's our acceleration. And also, under the same circumstances, it's easy to see that the acceleration of the second ball will be F12 divided by M2. Okay? Now, I'm going to say that the forces are not constant. Okay, F12 is not constant, F21 is not constant, but they are always equal and opposite. So I'm just saying forces are not constant. The balls compress, which causes the force to increase, and then they decompress, which causes the magnitude of the force to decrease. So F isn't constant, as a result, A is not constant, but, this kind of a disclaimer, we're going to pretend that they are. So let me just take this statement and kind of separate it from everything up here. But now we're going to say, okay, assuming that the forces are constant, I want to find out what's the change in V1, the velocity of the first ball. And then I want to answer the same thing for the second ball. Okay? Well, what's change in velocity? How's change in velocity related to the things that we've talked about and the things that we've at least calculated symbolically? Well, what's the definition of acceleration? It's the rate of change of velocity with respect to time. If acceleration is constant, and it would be if we assume that these forces are constant, then the average acceleration is equal to delta V over delta T, change in velocity divided by change in time, because that's exactly what we mean by an average rate of change. Acceleration is constant, so the average rate of change is the rate of change. So the acceleration would be delta V over delta T, meaning that delta V would be acceleration times delta T, so that the delta V of your first will be the acceleration of your first multiplied by your change in time, your delta T. And of course the acceleration of the first is F21 over M1 times delta T. And then we do the same for delta V2. And we find that that's F12 over M2. And that's equal to this. Okay, well, we go on. I think, is this it? No, it isn't. So we're going to stop here, and I'm going to find the right board, and we're going to see what the implications of this are.